Hello and welcome. This video will give you an introduction to double integrals. Here are the objectives of this video. We will talk about double integrals and what they are used for. We will also show you how to calculate a double integral. Let us begin by recalling some important concepts. In this graph, we have a function y equals to f of x, where there's only one independent variable x. Under this line that represents f of x, we have a shaded area A, bounded between x equals to A and x equals to B. Recall that to find this area A, we set up a definite integral like this. Integrating f of x with respect to x, and we set up the limits of integration to go from x equals to A to x equals to B. So in this topic of double integrals, you are expected to know and be able to apply the integration rules found in the maths formula card. Next, we recall that any surface in three-dimensional space, like this one here, is a function z equals f of x and y, where your independent variables are x and y. Here, we have an example of such a function z equals to 40 minus 2xy. This is part of the surface representing this function. When you substitute a value of x and y into a function, you get a value of z. The value of z tells you the height of the surface above the xy plane at that point. And this is the xy plane here. For example, at this point x equals to 1 and y equals to 4. Substituting these values in the equation tells you that z equals to 32. That is, this point on the surface is 32 units above the xy plane here. And at another point x equals to 3 and y equals to 2, substituting these values in the equation tells you that z equals to 28. That means to say this point is 28 units above the xy plane. We are now ready to begin our discussion on double integrals. Here, we have a surface S above a region R. The problem is then to find the volume below this surface S and above the region R. That means to say we are talking about this empty space between S and R. The solution is then to construct a double integral. Firstly, we let S be defined by z equals to a function of two variables, x and y. Then, the volume that we want to find, which is this empty space between S and R, is given by this integral or this integral. We refer to these as double integrals because, as you can see in this expression, there are two integration symbols. This expression also has two integration symbols. Furthermore, notice that these two integration symbols have lower limits as well as upper limits on them. In the next slide, we will explain these limits. In the previous slide, we had stated that either one of these integrals will give you the volume below the surface S and above the region R. Looking at the diagram, notice that A, B, C, and D correspond to the boundaries of region R. Along the x-axis, A tells you the lower boundary of region R, and B tells you the upper boundary of region R. Along the y-axis, C tells you the lower boundary of region R, and D tells you the upper boundary of region R. Notice that A, B, C, and D also appear in the integrals. Therefore, the limits of integration refer to the boundaries of the rectangular region R. Let us examine the first double integral. In the first double integral, dx comes first. Therefore, the inner integration limits, a and b, refer to the x values, which is also what the diagram says, where a and b are along the x-axis. Hence, we can write out the first double integral like this, where we place a pair of square brackets here and here. The integral contained within the brackets is known as a partial definite integral. This is because f is a function of x and y, but we are only integrating with respect to x only. Writing in this way, This tells us that in this double integral, we should be integrating with respect to x first, then followed by y. Let us look at the second double integral. Since dy comes first, therefore these limits c and d are for the y-axis, and you can see that this is the case in the diagram. Hence, we can write out the second double integral like this, where we place a pair of square brackets here and here. Again, the integral in the square brackets is called a partial definite integral. And in this partial definite integral, we integrate with respect to y first. Then, having completed this integration, we integrate with respect to x next. Let us now look at this example. Consider the solid S bounded above by the surface z equals 40 minus 2xy and below by the rectangle R defined by x between 1 and 3 and y 2 and 4. Now notice that you are asked to calculate two double integrals. We are now ready to evaluate the integral in part A. But first, let us understand what this integral means. You see here a 3D plot of a surface. This surface is given by the equation z equals 40 minus 2xy, and of course we call this surface the surface S. 40 minus 2xy is exactly what we are trying to integrate here in the integral. We also see that there's a blue region here, and this is exactly the region R. Now, at this point in time, we want to recall that a double integral gives you the volume between a surface S and a region R. And so this graph here is meant to help you visualize the volume that we are trying to find. Now, if we write dy first, that means we are integrating with respect to y first, and this integration limits 4 and 2, which appear on the inner side of the integral, refer to values along the y-axis. Hence, starting with 2 means that this line of region R is given by the equation y equals to 2, and this line of the region R is given by the equation y equals to 4. Next, we integrate with respect to x. These outer integration limits, 1 and 3, are then limits along the x-axis. Hence, this line of region R is defined by x equals to 1, and this line of region R is defined by x equals to 3. Now that we have seen a visualization of what this double integral means, we are ready to evaluate this double integral. Remember that we are able to place square brackets so as to identify the inner partial definite integral. So copy the rest of the expression, close the square bracket and write dx. So the square brackets tell you that you should integrate this expression 40 minus 2xy with respect to y first. So let's do that. Retaining the square brackets, we now integrate 40 with respect to y and 2xy to give us 2xy squared divided by 2. So with integrating with respect to y, we pretend that x is a constant. Now, we just write it here, the limits of integration, remembering that these are for the y variable. And so, you may now begin to substitute these values inside to evaluate the definite integral. Bearing in mind 2 divided by 2 is 1, so we simplify that. And we substitute y equals to 4 inside, minus 40 divided by 40 multiplied by 2, minus x 2 squared dx. We are ready to now evaluate and simplify. So this is 160, this is 16x, this is 80, and this is 4x dx. Simplifying this gives us the next line, 80 minus 12x. And now we have a simple, straightforward integral with respect to x, and we are ready to perform it. again, we are ready to substitute x equals to 3 inside. Simplifying 12 divided by 2 to give me 6 and 3 square. Now we are ready to substitute x equals to 1 inside. So 6 into 1 square. Now you are ready to take your calculator to evaluate these numbers, and you should be able to get 112 cubic units. We are now ready to evaluate part B. First, write the equal sign and copy the outer integral as you see. Now we write a square bracket and write in the inner integral. Once we have written dx, you are ready to write the other square bracket and write down dy. So now what happens is that we have a partial definite integral of 40 minus 2xy with respect to x now. That means that when integrating, we treat y as a constant. So we are ready to perform the integration. 40x, okay, write the square bracket here. And treating y as a constant, we integrate x, so that means that 2x squared divided by 2, and y remains as it is. And of course, the limits of the definite integral are for the variable x. Now, if you are afraid that you might be careless and substitute into the wrong value, then you may write out the whole limits in full by writing out x equals to 3 and x equals to 1. Write out dy here, and then you are ready to evaluate the definite integral. Now, okay, so we are ready to substitute x equals to 3. So 40 into 3, and 2 divided by 2 is 1. So that means that we just substitute x equals to 3 here, so that becomes 3 squared. And since there is nothing to substitute into y, we leave it alone. And we are now ready to substitute x equals to 1. So there we go. And 2 divided by 2 is 1, and now we just substitute 1 squared and y. Okay, so now we have this bunch of expressions, and we are ready to simplify. So this is 120, this is 9y, this is minus 40, and this is plus y dy. And we are ready now to simplify it further. This gives us 80 minus 8y dy. And now this is a straightforward definite integral with respect to y. So this is 80y minus 8y squared over 2, 4 and 2. Now, so we are ready to substitute 4 and 2 inside. So let's substitute 4 first. So that is 80 into 4 minus, okay, 8 divided by 2 is 4. And so 4 squared. And substitute 2 inside now. And 4 into 2 squared. And now again, you are ready to take out your calculator and evaluate. And again, you will see that this evaluates to 112 cubic units. We have now completed this example. Let us summarize the answers that we have obtained. In both part A and part B, we have the answer of 112 cubic units. We will have more to say about this result in the next video. But for now, let us test our understanding with the following questions. In this question, a function f of x and y is integrated over a rectangular region R. So this is the rectangular region R. X is from 3 to 9, y is from 1 to 5. Which of the following double integrals give you the volume of the region below f of x and y and above R? So notice that you have 4 choices here. You have A, B, C, D. Study the order of the dy and dx as well as the limits of integration, and decide which one is the correct one to give you the volume below f of x and y and above R. We are now ready to explain the answer. Now firstly, notice that the x limits of r are from 3 to 9. Let us then examine the integrals where we see dx first. So look at part C. Dx comes first, and therefore these limits of integration are for x, and we notice that they do not correspond to our region R. So we can eliminate part C. For part D, dx comes first, so these limits of integration are for x, and again they do not correspond to R. For part A, notice that the dx is here, so this dx means that the outer integration limits are for x, and again they do not correspond to the region R, so A is out. And for B, dx is here, so that means that the outer integration limits are for x, and we notice that these are the correct values of the limits for R. So let us check if this is indeed the case for y as well. So for y, the y values run from 1 to 5, and that means that the inner integration limits should run from 1 to 5 as well, and we see that that is truly the case, and therefore B is our correct answer. We are now ready to summarize what we have learned. The volume of the solid below surface S and above region R, here we are talking about this surface S and this region R, is given by this double integral, which means that we integrate with respect to x first, or this double integral, which means that we integrate with respect to y first. Either one of these will give you the same answer. Notice that if we integrate with respect to y first, then we write the limits for y inside the inner integral, and if we integrate with respect to x first, then we write the limits for x in the inner integral. Next, we also found that evaluating the partial definite integral gives you an expression for the area of a cross-section of the volume. So let us recall what this means. We have this double integral. Here we put the square brackets to isolate the partial definite integral. And after some working, we arrive at this answer, at minus 8y. And what does at minus 8y mean? At minus 8y is the area of the cross-section at any value of y. So choose the value of y between 2 and 4 and substitute it into this expression, and you will get the value of the cross-section at the particular value of y that you have chosen. With this, I end this video. Thank you for watching.